since I'm trying to learn this area myself, it will also help me. These questions will also help me try to get possibly a different perspective, or maybe I was wrong in some perspectives, because I've tried to abstract out some of these concepts. And I'd like to start a little bit with Shweta madam's kind. उन्होंने उनका दिल बहुत बड़ा है, उन्होंने मुझे न्योता दिया था. She sent me this kind invite. I'm a little bit of a over the hill researcher, and it's a bit actually like that old Pepsi ad. So I'll just get this video onto the screen. Most of you would be familiar with this Pepsi ad. This has Shah Rukh Khan, this came out during that time of the World Cup. So Shah Rukh Khan is desperate for a Pepsi, and he's trying to get into the league of the Indian cricket team, but no, obviously not the right way. Just as I'm trying to get into the league of good researchers, completely by fraud. Okay, so Shah Rukh Khan goes in and cites Pepsi there, and he's trying to hide, and then so he goes to Rahul Dravid and says, "Ha, Saurav, pile," and then he finds his favorite Pepsi, and then he's said to be on. You're on right now. The captain says, just like Shweta madam says, well, it's time for my lecture. And then so Sachin just takes the Pepsi, doesn't take the bat, and aha. So that is the issue here. So my talk will be a little bit like that. Okay. Shah Rukh Khan tried to mask, or rather, me trying to masquerade as a good researcher. So it also actually the story started with this obsession with chat GPT, LLMs, and transformers. Started with a 2017 paper, which was from Google Brain. And the interesting part is, unfortunately, Google Brain or Google Research, none of these authors are currently with the organization. I think that's also an irony. So this started, and the title of the paper is "Attention is All You Need." And for for over the hill researchers like me who are trying to get into a comfort level, suddenly something very new appeared, which obviously we need to know today. So instead of "attention is all you need," it basically came to "tension is all you need." And see, when the term transformers comes into play, what is it that we think of? Well, this is one of them. Okay, Transformers: Rise of the Beast. We've got Optimus Prime, Bumblebee, so on and so forth, who are out to save the world. The other interesting part about Transformers is this, and many of us have nightmares about this kind of Transformers. It's not just the voltage ratio being proportional to the number of turns, it's also the magnetic circuits part. Where is the current entering? What will happen to the mutual inductance, so on and so forth. This transformer was named because the initial idea in the 2017 paper was for English to German translation. Okay, because translation systems are one form of language understanding and a pretty important form for that. So the transformer that they are talking about is to transform a line of input text in one language to another line in another language. Now the interesting part is that this basic idea of transformers, the idea of self attention, of multi head attention, has actually extended to many aspects of signal processing, images, and videos as well, wherein some of these concepts are rather natural. I'll try to come to some of these issues and some points to think about, because that is what will give us a better grip on this particular topic. Now, if I look at the basic idea of next word prediction, predicting the next word which is supposed to occur, why is this an issue? Because this is there in our mobile phones as well, right? The moment we try to type, although मेरे दोस्त जो कहते हैं कि सुमंत्र तू तो टाइप नहीं करता तो टाइपो करता है. So it is more of like my typing is more of typoing, unfortunately. But see, it would have been worse had that next word prediction not been there in our mobile phones. However, if we look at a little bit of the history, it's more of engrams. So this was actually the year 2012. That's 5 years before the Transformers paper was a sort of a watershed year because the entire technology in natural language processing sort of changed. Okay, I'll come to some of these trends as to how natural language processing has influenced research in many other fields. And today it definitely is starting from transformers. Now, the the problem is not new. And in fact, the interesting part is that if I see both letters as well as words in any language actually do not appear at random. And this is something which was understood way back in 1913 by Russian mathematician and mathematical physicist Markov. And Markov, one of the things his study, 1913 study, showed that the probability of a letter appearing depends on the prior letters. For instance, in the English language, if I have a Q, the next letter following it has to be a U. Okay. So there are some, so in that case, the probability is very high. That's close to one. In some cases, there are, so the the effect is that letters don't appear at random. So there is some rule, there is some probabilistic rule, there is an uncertainty that is associated with it, and transformers today handle that part incredibly well and sometimes scarily well as well. In 1951, so from probability, a very natural line of a very natural thread of ideas actually goes to Claude Shannon, because Shannon introduced information theory, and he introduced functions like P log P to be a measure of information. So there are expressions involving entropy and many related concepts out there. So Shannon tried to characterize this as an entropy based formulation and look at predictions. He tried to do it for English letters. And the interesting thing is, even in India in the 1960s, Bhattacharya, so this is not Amit Kumar Bhattacharya, after whom the Bhattacharya distance, the symmetric Bhattacharya distance measure is named. That gentleman had his paper in 1941. That's a different Bhattacharya. So this gentleman was a PhD student of the same Mahalanobis, the founding director of the Indian Statistical Institute at Calcutta, and he was actually the first. He actually established the first institute for statistics anywhere in the world, and he was also founding father of many techniques in statistics, which actually helped India's growth, like the 5-year plans, okay, and all the statistical analysis that went with it, including algorithms. So one of the things Bhattacharya studied was a statistical analysis of Tagore's Nobel Prize winning Gitanjali. Okay, so this study had been around for a very long period of time. Until 2012, the state of the art, as I mentioned before, was what are called n-grams. And n-grams is still the technology behind prediction in mobiles. It's a simple probability based prediction because the mobile phone processor is not that powerful. Secondly, mobile phone storage is at a premium, cannot store that much. So the idea is that with very little memory footprint, it is possible to do some level of prediction. And one of the things that we would have observed in mobile phones is that this prediction often gets the sentence grammatically incorrect. Okay, it simply blindly predicts the next word that is going to come. It gives a choice of three words, typically on WhatsApp, for instance. Okay, the sentence could end up being grammatically incorrect. However, with ChatGPT, one of the things that we've seen is that sentences, at least given problems associated with transformer architectures, LLMs, like the problem of hallucination. So, this idea here is that at least sentences will not be grammatically incorrect in ChatGPT. The training is such, and the basic methodology is amazing. So what n-grams typically do is make a prediction based on the last two or three words. It's typically causal in nature. So prediction finds its application in things like words, weather prediction, financial prediction, and in fact, knowing if somebody claims to know the weather well, see, climate is easier to predict. Weather changes and therefore weather prediction. See, nobody does climate prediction because climate is something like a time integral. It is well known. Okay, the climate of a place, although climate is changing, but it's changing slowly. See, this is the Fourier way to look at life, and in fact this is the ancient Indian philosophical concept of the jad and the chetan. The jad is either the unchanging or the slowly changing part of the world. The chetan is the rapidly changing part of it. Okay, so climate doesn't change, at least doesn't change very rapidly, and thankfully so. On the other hand, weather changes, so it is important to predict weather well in advance, and sometimes it's a very difficult task. So words is much easier. Weather is very difficult. Then knowing the market, that is developing a portfolio or doing what is called high frequency trading, is very tough. What does it mean to know a language well? Because that is what we are concerned about with regard to transformers, LLMs, and ChatGPT. So knowing a language well has got quite a few repercussions. When does one say that one? It's even true when one tries to learn another language. So for text prediction, it means what is the next word to follow. But the key part is in context. The sentence has to be grammatically correct and the sentence has to maintain context. I'll come to lots of examples of that. For instance, the English language contains many words which have completely different meanings in different concepts. The term bank could be a place where financial transactions are done. It could be the bank of a river. It could be the angle at which a road is constructed so that cars don't slide off it when they are let's say taking a turn. It could be question and answer sessions. So today, this is, for instance, one of the biggest applications of technologies which use large language models, automatic chatbots. For instance, if you have seen, let's say, on the Air India website, Air India has an excellent chatbot. Okay, then one important application of large language models, knowing a language well, is summarization. Is it possible to find the political opinion of a person from his or her social media, like Twitter, from his or her social media posts? Then machine translation. This has actually traditionally been a challenge. This research actually started sometime in the 1960s, the 1950s, and the 1960s. So this was the point in time when McCarthy had coined the term AI, and the reason was actually very simple. That time, see, this was the height of the Cold War, and in the US, what they found out was that there were very few people who could speak Russian fluently. They could even a basic understanding of Russian was at a premium. There were not enough people for that. So the idea was to somehow have computers and AI based systems to make that machine translation between languages. So English to Russian, Russian to English. Because if they intercepted, let's say, wiretaps, if they intercepted communication which was in the Russian language, it had to be translated to English. Then, of course, there is sentiment analysis, and this is something which some of my friends around me are also working in. So, given a scenario, let's say a chat, okay, is the sentiment positive? Is it negative, or is it neutral? So, because in a country like India, where access to even basic healthcare is limited, if on the other hand the penetration of mobile phones into rural areas is actually quite deep, it's actually quite deep nowadays, and even if we refuse to believe it, the level of literacy is yeah, it could have been better, but for instance, electrification is actually quite a lot. Just hold on, just hold on. Sorry, that was a. So in this case, see here the idea is that let's say for instance the stress levels which students are going through, is it possible that a person has suicidal tendencies so that it can be referred to? We spend a lot of our time being online, including youngsters, and for instance these are technologies which youngsters actually use quite well, much better than us. So is it possible for for an app to sort of have this understanding as to flag this issue of concern to a relevant doctor? Or let's say nowadays what people are trying in rural areas as well. For instance, if you look at some of the work of the IIT Patna group, the husband-wife team of Dr. Asif Iqbal and Dr. Sriparna Saha, and so some of these things which they are actually looking at nowadays is to have bots with some form of emotion in them, wherein you can talk to a bot and have the bot actually express things like empathy, sympathy. So this is Alfred Adler's scale. Compassion is one level, empathy is even more, sympathy is even more. So can that be incorporated based on what the chat is? So people are looking at these sort of applications. So it will be a bot which which can actually help. It can it can talk almost with human like emotions, and as well as collect information, because if I at least trust the bot, if the bot is giving me strange replies, I'm not going to put in something like I'm getting hallucinations or these sort of thing. I'm not going to tell it to the bot. That's the idea. So, a little bit of an introduction to this. As I mentioned before, that is, the prediction on a mobile does not actually encode context. It might result in some weird sentences. Even the syntax need not be correct. What it does is it's based on n grams, where n is 2 or 3 typically. It simply predicts what word is most likely to come up after the last couple of things. On the other hand, transformers, they actually keep track of the semantic context of what is being written. Sorry, you can see that I've actually typed this document in a huge hurry and there are lots of typos. The point is coherence. And transformers typically, let's say GPT-4. Okay, so the amount of training data is incredible. And today, in fact, Open AI, there's very little open about Open AI. The sort of hardware that these researchers have access to, it's actually become completely monetized, and it is only the purview of a few organizations who can actually afford. We in educational institutes have no chance of almost competing with them unless we contribute a theoretical at a theoretical level, and that extends to that extends to let's say universities in well-to-do countries as well. Okay, so for instance, if I ask a chat GPT like system, if I tell it write a story, then the reply could be once. Okay, then the next prompt would be write a story starting with once, then it will prompt upon. Okay, then if I give the previous one is actually an input to the next one, write a story once upon, then the chat GPT one will prompt with a, then write a story once upon a time. Okay, so what it's doing is it is not just giving a grammatically correct statement. In many ways it's semantically correct because uh, the issue of context has actually been accounted for. Then the next one is write a story once upon a time, then there, this is what chat gpt prompts us with. So if the input is write a story, now what is it in chat gpt which is actually helping? What is the basic architecture? The basic architecture, one of the basic concepts which is involved here is tokenization. And at least in computer science, the term tokenization is something that is well familiar with, let's say, people who have taken a course in compiler design. Okay, so the first step is often tokenization. That is, whatever is the input text, it is converted into a set of tokens. The second step is Embedding. Embedding is an internal representation because, after all, see, after 2012, this is the point where people started applying neural networks to problems in natural language processing. Why is this different? I'll come to some of these issues. Why is this different and why is this difficult? See, neural networks typically work with numbers and they don't work with categorical variables like words or, let's say, tokens. They don't really work well with that. So, since 2012, this was when Word2Vec came about. So the idea there was, since then, people started using neural networks for computer science issues, which they actually dealt with categorical variables and not numerical variables. The next step typically is positional encoding. Positional encoding is the same words in a sentence can carry completely different meanings if the words are jumbled up. It's quite unlike a very, very well formed language like Paninian Sanskrit. Because in Paninian Sanskrit, even if the subject word, if the subject, the verb, the object, these are changed, the sentence essentially carries the same meaning. But that's not true for modern natural languages. That structure is just not there. After that, there is there's essentially an encoder decoder architecture wherein, with the information about the tokens, the LLM or the transformer is going to have some internal representation, and the encoder part actually has a cascade, a set of cascades of two blocks. First is attention, followed by a feed forward neural network. So this is the attention that we are going to talk about. What we will see is that the attention that came from the transformers paper is actually a scaled distance. Okay, we'll see how it's a scaled dot product, which actually gives attention. And gives attention is, we might want to multiply it by, let's say, a number between 0 and 1, which implies how important is that, followed by an ordinary feed forward neural network for the prediction, let's say, and followed by a softmax, which actually gives the probabilities. So this is it. There are some of these blocks. Here in this example, I've taken 3. In the original Transformers paper, there was an implementation with 6 blocks. After that, as I mentioned, there's the softmax layer, and the output of that is ones. Okay, so this is the way that write a story. So the output comes here as ones. So let's look at the first step. So the idea here is, in fact, this tokenization has been around in natural language processing even before 2012. For instance, some of the part of speech tagging, or the POS, what's called the POS tagging, takes every word, prefix, suffix, punctuation signs, and maps them onto a known word from a library. Okay, it takes in all words of a dictionary and all usages and then maps it to a particular token. Now, here, large language models are typically language specific. So, an LLM for English is not really going to work for any other language, or let's say an LLM for English to German translation may not work with others. And some are also domain specific, like the vision transform. Okay, wherein the tokens are actually based on a part of an image or a video. Okay, there's a vivid also. There's a huge amount of training which is involved. This learns the structure of sentences or images or videos, as the case may be. So if I give it an input, write a story, basically a large model would split it into tokens, write a story and then a dot. So this actually reminds us of one of the first few places where we have seen tokens. One of the first places where we see tokenization is, for instance, in a lexical analyzer of a compiler. So when, let's say, a program is given to a compiler, one of the first things that happens is lexical analysis, where, for instance, if I have F, O, and R, so there is a very simple finite state machine model. It's typically a Moore machine or a Mealy machine and not a DFA as is taught to us in textbooks. Why? Because the DFA is a machine model which does not have any output. On the other hand, a Moore machine or a Mealy machine typically is a finite state machine model with outputs. So the idea is that the output of this is that once I reach this state of the finite state machine, the finite state machine has to give as output a token for the keyword for. Okay. And it's also something like, if I see this particular thing in a programming language like C or C++, the idea is this is a keyword, this is a variable, this is another variable. So int, var1, var2. So the idea is this is tokenization, and this also actually gives us one of the usages of ChatGPT today. And most of us teachers are absolutely scared of the spread of ChatGPT because our students use ChatGPT to also write computer programs and submit assignments for that. So this is the point which I was trying to mention earlier. That is the electrical engineering and computer science conundrum. What is so electrical engineer has actually given electrical engineering has actually given quite a few concepts to computer science. So dynamic programming started with discrete time control, some of the theories developed by Richard Wellman in the 1940s during World War II. Then the concept of graphs. The concept of graphs, in fact, graph theory is getting back into electrical engineering, but a lot of it actually started with electrical engineering. For instance, if one is doing PCB design, one needs to have the connection between the components. One has to have a planar graph. So planarity testing. It started off with mathematicians, it started off with puzzles and, let's say, the Konigsberg Bridge problem, and which actually has been formally codified as nowadays as the traveling salesperson problem. These are all related issues, the Hamiltonian paths in graphs. Then automata theory has again come from electrical engineering, because the interesting thing is, if I can create a finite state machine for lexical analysis in a compiler, I can actually implement it on a breadboard. Okay, this is actually fascinating, because all that I need to understand is that the alphabet, I need a binary representation for that alphabet. It's something like saying that I've got a ASCII representation for every character, and that, so I can actually have a full lexical analyzer on a breadboard. If I append this with a stack, I can also have a full parser on a breadboard in hardware. Now, on the other hand, CS has also given us some very interesting things, very specifically with natural language processing. CS has given us techniques such as latent semantic analysis. So this was pretty popular in the the early 2000s and sort of mid 2010s. So this is latent semantic analysis or probabilistic latent semantic analysis. There's latent Dirichlet allocation. There's the Chinese restaurant. See, all of this has actually come from models which involve a hidden state or a hidden concept. And this also started with the basic concept of an SVD. Okay, having a matrix and then splitting that into three components, wherein the middle component, that rectangular matrix, would be the matrix of singular values. So this is the idea. So from a non-numerical start, essentially with categorical variables, people tried to characterize this as if this were a singular value decomposition problem. And now transformers have basically transformed the entire world. So the basic difference, as I see it, between a computer science representation and an electrical engineering representation is a coarse-grained one for computer science, using categorical variables which do not have a very natural mapping to vectors of numbers, and fine grained numbers in electrical engineering. So there are many similar concepts. In computer science, there are characters, and one talks about string matching, whether there is a match or not. In electrical engineering, one talks about correlation between, so sorry, I think there is a there's a typographical error here as well. Correlation between two signals and the degree of match. Okay, so the basic concept is pretty similar and one can influence the other. Now, one of the things that often troubles us is how can I, for categorical variables, how can I map a word to a set of numbers? So, suppose so we'll start with a couple of completely artificial examples. Now, before transformers, one of the standard ways wherein computer science and natural language processing handled these issues was with what is called a one hot encoding. So, if let's say I have three food items, I've got pizza, I've got a burger, and let's say I've got cake. Okay, so one of the very natural ways to represent it, if my world is just these three, has just these three entities, then I can represent them as one of the possible encodings is 100, 010, and 001. This is a very natural way to represent these entities. Now, one is also talking now about millions and billions of words, that is, all words in a dictionary. So this sort of representation will not really scale up. Okay, the vectors, the vectors are going to end up being very very large. And what does one do? So the idea is that one needs to look at a semantic space. Now let's first start with a couple of absolutely handcrafted examples. So suppose I've got calf. Okay, suppose I've got a two-dimensional space and a word calf, and I've got a word puppy out here. Let's look at these concepts. I have a word dog. Now, one of the things is if one, so one can sort of guess that age will be a parameter along the x axis. Okay, puppy to a dog, size would be a parameter on the y axis. Then where would cow fit in? So, cow, it's actually intuitive that cow is going to fit in somewhere here. So first, let's try to develop these concepts intuitively, and then we'll try to think about how ChatGPT does it, how do LLMs do it, how do transformers do it. Okay, so in this case, two features, age and size. So for a puppy, age is low, size is low. For a calf, age is low, size is reasonable. Then for a doggy, age is high, size is low. And for a cow, which is essentially we wanted to note where would cow fit into a two-dimensional semantic space. So one of the things that you recognize at this point is that the one hot encoding is not really going to be sufficient to encode these concepts. Okay, because embeddings, this is one of the key points to understand. Embeddings also capture analogies and relations. They are intrinsic. This is the way that semantics is built into natural languages. Let's take another completely handcrafted example. Let's look at movies. So there are this particular example is taken from one of tutorials by Serrano. You've got Meal, then Rush Hour 2. Okay, that Jackie Chan action and comedy series, then Taken. So some human interpretable cases. Okay. So what one does is in a setting, if there is a human interpretable case for it, we can try it. What ChatGPT does is it uses a simple distance measure. It uses many iterations and initializations and has come to some embeddings which are fairly standard. Now, once again, if we have two axes, let's say one of them is action. Is the movie an action movie? The other is, does it have, let's say we are looking at IMDb, and IMDb typically gives genres of movies, and a particular movie can fit into more than one genre. It can have action, it can have comedy as well. So for this sort of a situation, you've got Male. Okay, there's hardly any action. There's that lovely do you remember this movie, Tom Hanks? And there's a lot of comedy in that. Then Rush Hour, there's that Jackie Chan series. There's a lot of action. There's a lot of comedy as well. Then There is Russia 2, which came after that. So lots of action, less of comedy because this sort of became a bit predictable. Then Taken. This particular movie has a huge amount of action and there's nothing really funny about it. Now comes the concept of positional encoding. This is an important concept. Why is this important? In fact, this is one of the examples that I had taken right at the beginning. That is each token. Now we are not going to talk about words, but we are going to talk in terms of tokens. Okay. So each token now is represented as a vector of numbers. A let's take a completely synthetic and a handcrafted example once again. Let us take a two-dimensional world with technology on the x-axis and a parameter fruitness. How much is a thing, a fruit, on the y-axis? So if an orange comes in, so an orange hardly has any technology, okay, and it's relatively high on the fruitness scale. Then if there is a cherry, then it's high on the fruitness scale and apparently needs a bit of technology also in order to grow it, harvest it, so on and so forth. If there is a phone, then a phone is definitely not going to be anything close to a fruit. It's high on technology. This is a mobile phone. Now, an orange, for instance, in this, I can start with its coordinates being 0, 3. A cherry will have coordinates 1, 4. The phone is going to have coordinates 3, 0. These are arbitrary numbers. The idea is that ChatGPT with arbitrary random initializations actually gets to what is finally consistent across millions and billions of iterations. Now, let's get back to our original example. So, for instance, right. So, it's not really the word right, but the token corresponding to the word right that will have a feature vector associated with it. Okay, this could be in a very large dimensional space. ChatGPT started, for instance, with 512. Okay, so this is a vector of numbers. A, a corresponds to another vector of numbers of the same dimensionality, and we might use some dimensionality reduction techniques to get smaller representations. Write a story. So story would have another vector of positive and negative floating point numbers corresponding to it. And this full stop has another one. So they're all vectors of the same size. Now, a sentence of words is also a vector, wherein each word is also a vector. And one very interesting representation is that the sentence could possibly also be an entity of the same dimension as a word, but in taking the most important, let's say 512 features out of them. That's the idea. So, what is the attempt? Now, if I want to combine two tokens like this, the tokens corresponding to two words like this, one can try one can try many things. So basically, how do I get a sentence out of different words? One way is to add these component wise. So if I've got two vectors, 1 comma 2 and 3 comma 4, I get 4 comma 6. So here, see, this is out of words, I've got one representation for a sentence. Now there is a problem. What is the problem? The problem is that addition is commutative. Okay, the order in which we add two numbers is not fixed. So if I had two words like 3 comma 4 and 1 comma 2, then the sentence would also have a representation 4 comma 6. So now do you see the ambiguity? Although these two sentences could mean completely different things, the representation is actually the same. So this is not a very good representation at all. The examples are, the typical example here is I'm not sad, I'm happy. And I'm not happy, I'm sad. They mean two entirely different concepts. Okay, they have the same set of words as you can see, but the important part is what appears where, and that is getting the context. So addition is not going to work. So the semantics essentially gets lost. That is, two sentences with entirely different meanings should give two different vectors, but with additions, they seem to give the same one. One possible solution is what transformers resorted to, and ChatGPT also uses that. That's called positional encoding. It's not that we haven't seen positional encoding before. One example of positional encoding, which everybody is familiar with, is, for instance, for decimal numbers. So if I have a if I have a binary number 1001, now every bit has a position and a weight associated with it. Okay, so in order to get the decimal number, which is going to be unique for a binary number like this, one has encoded the position of that bit in the bit string. So do you see how this has positional encoding as an intrinsic concept? This does. Another example is a binary tree. A binary tree, for instance, can be represented as an array and has a unique representation where for node I, where for node with index I, its left child will be at 2i plus 1, its right child will be at 2i plus 2, where I starts from 0. Okay. What else? This is exactly what I talked about. So one has these representations, one has unique representations. So this is again positional encoding. The idea is that the encoding encodes the position of an entity in the structure. In this case, this is a much more complicated structure. It is a two-dimensional structure. So that gets encoded in a one-dimensional pattern. Now, one of the main things in the transformer paper is the concept of attention, and the way that transformers model attention is actually a scaled dot product attention. So let's see what that is. In fact, if you read the transformers paper, it is a very abstract and a not easy to understand paper because it suddenly introduces a lot of concepts. Most of them are ingrained in heuristics. And what it does is it proposes a lot. Okay. So it's actually a bit difficult to understand. But if we abstract out some of these concepts, it becomes relatively easier to understand it. So for instance, in the paper, uh, they've taken they've taken vectors for queries, for keys, for values, represented those vectors in matrices so that all of those dot products happen, at least some of them happen together. So that gives rise to their concept of essentially a scaled dot product attention. Now, this can actually be abstracted out in order to understand what these things are. Let's see what these things are. So rather than bother about what are queries, what are keys, what are values right now, let's look at the basic idea. The idea is that attention clarifies the context. That is, words can be close in feature space if the context is clear. The example that I gave some time back also was the word bank. So if I'm talking of the bank of a river, then in this semantic space, the representations for bank and for river would move close. When we are trying to have a system which has these two words as a part of the vocabulary, then money in the bank. Here, for this context, bank and money move close to each other. Then the bank of a road, the angle of banking. Here, bank and road would move close to each other. And we also have to remember that for bank, in this case, we have three representations. So in the English language, in this example, there are three representations of the word bank. And it is important to store all of these representations. It's not that we can go ahead with one of them. While training, depending on the context, we will have one interpretation of bank being closer to river, the other interpretation of bank being closer to money. As we are training, the other interpretation of bank getting close to road. But after the system is trained, when we are using it, so depending on the context, we will choose one of the interpretations and then go ahead with that. This is the idea. So that word bank carries information of the neighboring words. That is, it also carries the context along with it. Another example. Let's say the sentence is a tiger in the green woods or tiger woods in the green. Okay, they are completely different sentences, one of which may make sense to a person who's dealing with biology, a zoologist who's looking at a tiger which is moving about in the jungle. And the second sentence might be of interest to a sports person or a person in golf who's looking at famous golfer Tiger Woods in the green, that is on a golfing ring. Then there are differences between tasty apple and dependable apple. So tasty apple would point to a fruit, and dependable apple, for instance, would point to either a mobile phone or a iPad or a MacBook. Okay, this is the idea. This is the very basic idea behind the multi-head attention. That is, there are many different embeddings which could correspond to a word, and these are used to modify vectors and to add context to them. This is a pretty interesting concept. Now let's look at some of this. Let's look at, see, this is the, we are trying to look at a basic building block of a transformer, which as per the paper has two blocks. One of them is an attention block. Okay, there is a concept of an attention, that is closeness in semantic space, and this is typically based on a dot product. What we are going to see is how the dot product comes in. Now here, there is also, we mentioned that there is an attention block, and after that there is a simple feed forward neural network for predicting the next word. Now how does this happen? It's actually interesting that why are we using softmax? We'll also try to justify that. The idea of softmax is that finally what one wants to end up with is a probability. And then from all the words in the dictionary, we want to choose the next word as one which has the highest probability. Okay. So for instance, for write a story gets into the transformer, softmax, and then what happens? The next word, let's say all the words in the dictionary are here. Okay. And all of them have a probability score which is associated with them. As you can see, these are the words from the dictionary in lexicographic ordering. It starts with aardvark. Aardvark is an animal with a long nose. Starts with AA and possibly ends with a word which has ZY. That's how a dictionary goes. Now, all words of a dictionary get a probability score based on the softmax because this raises a number to an exponential and then it normalizes it. At the moment, let's remember just the normalization part. We will see how this technology comes in, how this works. So, what Chat GPT or a large language model or a transformer does is it finds the word with the largest probability and then it gives it out. So for an input as write a story, it starts with once. And then the previous input, the previous string till now is an input to the next iteration. Then the next time it will be upon. So some of the lighter models of transformers, the free models will also give you these scores, will also tell you which are the words it has established a probability mass function over and which is, let's say, for instance, the second highest probability word. Okay. Now, there is another interesting part in transformers, that is after the main training is over, is there something else to be done? This is actually a very interesting concept because this is somewhat like the way that we human beings deal with this. What is this? It actually depends on the application. Okay. Wherein if we are, let's say, training a transformer for a chatbot application, then it should be trained on large data sets of conversations. If we are using it to help to write stories, poems, or even what our students do to write code, the training has to be a bit different. Okay, the general training could be pretty similar, but after the system is fairly well trained, the idea is that there has to be some post training, another training regime. This is why is this natural for human beings? Let's say one has an exam, one is in school and one has a sessional exam or a half yearly exam. So the student is going to prepare his or her subjects, all of the subjects, but there is also this is the general training. But then let's say before the history exam, the student, for instance, is not going to see formulae which were applicable for mathematics. So he or she would study the history part of it before that. But his or her general training would be for all subjects. This is the idea. An example is, suppose the a question is asked, what is the capital of Algeria? The internet is not necessarily the best question and answer repository. So training a large language model is fine, but if one wants to use this for a chatbot, there has to be a post training phase wherein there is a second training which is based on the context. And the internet is often the not necessarily the best repository for question and answer sessions. For instance, the next sentence after what is the capital of Algeria on the internet could be what is the population of Algeria. Now, this doesn't help answer the question. So, do you see that? It's like preparing for a maths exam, okay? Using essentially starting off with a cheat sheet of important formulae in maths while going towards the history exam. It's not of much use. That is the point. So the next sentence could be after what is the capital of Algeria could be what is the capital of Burkina Faso. So what is the idea of the large language model? It simply mimics the training set. It simply mimics the internet or the data set. So post training, after a general training session, it is again trained on a large application specific data set. For instance, for a chatbot, it is further trained on question and answer repositories. It's like humans. Okay. Now let's pay a little bit of attention. Remember, I was talking about the transformer blocks, let's say in an encoder of an LLM. The, the basic blocks in the encoder are first is an attention block followed by a feed forward neural network. And putting these things together, it's like saying that the attention block would essentially be the scaled dot product representation, which is what we are going to pay attention to right now. And after that, we will talk about the feed forward neural network, what it does. So once again, let's start off from a completely artificial example. So this is that familiar example of two axes, tech and fruitness. So orange is here at 0, 3, cherry is here at 1, 4, and a mobile is here at 3, 0. So if I look at a dot product is actually a measure of similarity. Why is that so? That is actually because a dot product is sometimes called a cosine distance. We'll see that. So an orange, yeah, these are the values here. I've also color coded these words. So if I take cherry dot orange, what is that going to be? It is going to be 0 into 1 plus 3 into 4, which is 12, which is a relatively high number. And we expect it so also, so that these two concepts are close by. Okay, so the dot product is high. On the other hand, if I take a dot product of a cherry with a phone, so it's 1 into 3 plus 4 into 0, the answer is 3. If I take orange and phone, okay, this is exactly 0. So this is less. So this actually, so one of the take home points at this stage is that a dot product is a measure of closeness. Okay, so if a dot product is low, the two words are very far apart in semantic space. If the dot product is high, the two words are close in semantic space. Now, this is what is given. Now we can have ambiguities. The so here this is the other interpretation. The other interpretation is one of an angle. They actually are very similar because if these two are normalized, we essentially have the cos, okay, as being indicative of the dot product. And we also know that because if I take two vectors A and B, their dot product is the magnitude of A into the magnitude of B into the angle which is between them, the cosine of the angle. So these are the values which come out of taking these dot products. For instance, here the angle between orange and phone is 90 degrees and cos of 90 degrees is 0. So they're actually the same concept. This is exactly what I mentioned. Now, what the transformers paper introduces is the concept of a scaled dot product. That is not just take a dot product, but also scale it. Now, this is a very interesting heuristic or a jugaad, what we call in the chaste vernacular of the region here in Delhi. What is this? What is this scaling? And the interesting part here is that this is a heuristic actually which has actually a good amount of theoretical basis also behind it. We will see here. So if you're familiar, for instance, with one of the concepts in dynamic programming is string matching. Now, if you have read Navarro's paper on string matching, Navarro also introduces a concept of normalized string edit distance. In normalized edit distance, this says that the edit distance or the score, it can get large if we are dealing with trying to match two large strings. So there is a normalization which is involved here based on the length of the strings. So the heuristic which the authors of the transformer paper use is we divide by the square root of the length of the vector. This helps keep numbers in the dot product. It helps them keep well in range. Okay, this is it's actually a heuristic to scale down large dot products, but is actually fairly well grounded in theory. So this is the Guimero Navarro paper that I'm talking about. So if I look at cherry dot orange, I'm going to divide by the square root of the length. So that's 2. So that's 8.49 instead of 12. So one of the things that we see is that the number has reduced. If I take cherry dot phone, so instead of 3, it's 3 divided by root 2, which is about 2.12. And orange dot product with phone, if I take a scale dot product, it will remain at 0. So let's look at it here. Suppose now we have ambiguity. And ambiguity comes in, let's say there is an apple. So apple could be an Apple device or it could be a fruit. And here context would be important. And both Apple initially in the initial training part without the context, all apples are, let's say, would map to an intermediate point. So there is ambiguity here. Now for this example, let us take another axis wherein we've got a representation for and, words such as and an. So now we have three axes: tech along the x-axis, fruitness along the y-axis, and others, let's say along a z-axis. So all our previous entities, orange, phone, apple, the ambiguous one, they are all along the fruitness and tech plane. And we have these connector words and an, let's say, located here. This is a completely handcrafted example. Now, if you're wondering how does ChatGPT do it, the way that it's done is basically in the training part. Remember that they train over everything that is available in the internet, or at least a very large training set. They've got numerous start points, all random, and they amortize the results over all of these iterations. So what people do is they remove a word and then try to reconstruct its representation. So this exercise has spread to an incredibly large number of words across an even more incredibly large training regime, results in a sort of fixed vector representation for this representation, one unique representation for any unambiguous word. For ambiguous word, it has a couple of representations. Okay, so let's look at distances now and how they change according to concept. So if we put these distance values here and construct a table, so this is what we got in a table by looking at the three-dimensional space that we constructed. We have got one axis for fruitness, one for technology, and another for others. So if the sentence is an apple and an orange, so how will these numbers change? So with this sentence, let us try to look at what are there. So we have taken orange, we have taken apple, we have taken and, we have taken an. Okay. For apple, this is what it is. Okay. For and, it's essentially, it's not got any contribution from, look at and, it's not got any contribution from orange or apple. There's no phone here. Similarly for and. So now we can normalize this. So an orange representation of orange is 1 times orange plus 0.71 times apple plus 0 times and plus 0 times and. Similarly, the representation for apple is 0.71 times orange plus 1 times apple plus 0 times and 0 times and. For and, it is 0 times orange plus 0 times apple plus 1 times and 1 times and. And similarly for an. So as you can see, and an should end up with the same representation if this is the sentence that we are considering. And if on the other hand, the sentence were an apple phone, okay, we start from this whole square table and look at what the changed values, if the context changes, would be. So these are the three words, okay. We pick up those corresponding numbers as we did before. So what will phone end up being? 1 into phone plus 0.71 into apple plus 0 into apple will end up as 0.71 into phone plus 1 into apple plus 0 into an. And an is going to end up as 1 into an. Now, for every sentence, these numbers would change. Okay. So there is a need for normalization. So what is the normalization that we are talking about? Because see, normalization is important because if these numbers get too large, we need to normalize them. Now, for normalization, one standard normalization trick is that all coefficients should add up to 1. So, for instance, for orange, instead of looking at orange as 1 into orange plus 0.71 into apple, we look at it as a linear combination. 1 into orange plus 0.71 into apple divided by 1 plus 0.71. So, this ends up as 0.58 times orange plus 0.42 times apple. Similarly, if we had now these numbers, remember the first example, these numbers need not be all non-negative. These numbers could be negative as well. Now what if we had an example wherein an orange was 1 times orange minus 1 times bike? If I want to normalize this, what is going to happen? Unmitigated disaster. Okay. सब कुछ बिगड़ गया. Now there is a requirement then that while the vector representations could also involve negative numbers, let us end up with positive coefficients, non-negative that is, and let us respect the order. That is, a number which was large before normalization should remain relatively large. Okay, it should suddenly not become small. That is, the function should be monotonic. Now here, this is where softmax comes to the rescue. So that feed forward neural network is followed by a softmax, which gives the final probabilities. So the mapping is x maps onto e to the power x. So instead of taking x alone, okay, what was the problem with taking x alone? We could end up with an unmitigated disaster like a division by zero. So let's look at what happens to orange then. Instead of 1 into orange plus 0.71 into apple divided by 1 plus 0.71, it ends up as e to the power 1 orange plus e to the power 0.71 apple divided by e to the power 1 plus e to the power 0.71. So this ends up, look here, this ends up relatively close to what we would imagine had we done an ordinary normalization. Similarly, for the second example, if let's say this was 1 times orange minus 1 times bike. So this problem does not arise here, as you can see. And as you can see, the relative order of these numbers still makes sense. Now, what happens to that other example with softmax? So an orange was 0.57 times orange plus 0.43 times apple. Apple is 0.43 times orange plus 0.57, sorry, and is zero point 0.5 times and plus zero point 0.5 times and. So this sentence changes these numbers. And with softmax, the sentence an Apple phone now gets a newer representation for the tokens corresponding to the words. So this is the new representation with softmax. This is for Apple. This is for and. And the disclaimer here is that we are making an approximation actually because softmax is slightly different. Softmax does not map a zero to a zero. It maps it to a small number, but it doesn't map it to zero. Okay. So this is what comes out of it. Okay. This is what we are essentially doing. So the zero, it cannot really be taken out. Instead of that, we've got e to the power zero, which is actually one. Okay, so the orange would end up being earlier. Earlier we had a case where these would, because these were zero, these would not form a part of the representation at all. But with a softmax, these would take away some of the probability mass, in fact 30% in this case. But this is what we have to live with. Okay, but suppose we use 0 going to 0 as an approximation, then an apple and an orange. So earlier, what was it? Without that approximation, we had these 0.15 and 0.15 out here. Okay. So here, an apple and an orange, this would end up as 0.43 times orange and 0.57 times apple. So the coordinates of apple in the context where we are talking about fruits. So this is where the semantics also comes in the context. The coordinates of an apple become 1.14 and 2.43. On the other hand, if the sentence is an apple phone, the coordinates, assuming that the others are zeroed out, that becomes 2.86 and 1.14. So let us try to visualize this. So initially we had an ambiguous representation, like orange was here, 0, 3. The Apple phone was here, 3, 0, and 2, 2 was the ambiguous position wherein an Apple phone or an iPad or a MacBook mapped here. Similarly, the fruit apple also mapped out here. What happens now is, given the context, now these two shift. Okay. So if you look at the little animation here, so they shift linearly along the line which joins the 2 points, the corresponding points here. Okay. So they've separated out. This is the idea. All right. At now, I think I've got only about 10 minutes more. So I guess I'll try to close the lecture around this time. So couple of closing notes. Closing notes are I've only tried to concentrate on some of the basic ideas. I haven't talked about nitty gritty details at all. I just haven't talked about them. That is, what are these? For instance, what are the keys? What are the values? Okay, what are queries? Now it turns out that these queries, values, these essentially are vectors of numbers. And in the Chat GPT example, sorry, in the transformers paper, they were all of the same length. All right. So I'm not giving these nitty gritty details. So what I've done in a way is, जिसको हम यहाँ पे दिल्ली वाले कहते हैं पतली गली से चले जाना. So I have essentially done a Pythagoras. Doing a Pythagoras is taking a shortcut. That is, instead of going like this, I've taken a shortcut. And it's actually a pretty involved and a slightly difficult topic to understand. I also don't understand it fully. I'm trying to grapple with it, but I thought of trying to learn it by starting from the basics. It's like saying this person gives a, ये बयान देते हैं, transformers isn't stressful at all. Okay, who says this? This is Josh, who's only 25 years old. ये देखिए क्या हालत हो गई है. And don't take my word for it. Please try to read much more on this. Try to read whatever tutorial you can find on the internet. Have a look at the very basic paper also to take things into consideration. So don't depend too much on what I have talked about today. So the joke is, let's say I call up an insurance agency because I've just hit something with my car, saying I hit an animal. Am I covered? So the insurance agency asks, what did you hit? My reply is a fish, because this is actually what has happened. Okay. So jokes apart, I guess I'll stop speaking at this particular point in time, uh, because there's very little time that has left. So time for, I'll switch my camera on so that you can see my befuddled face when you ask me a difficult question. So yeah, please feel free to point out mistakes. कहने को तो मैं कह सकता हूँ कि हाँ मैंने जान के गलतियां की, लेकिन अधिकांश गलतियां अनजाने में होती हैं. And things that I know, I'll simply raise my hands and say that, well, I'm sorry, I don't know. As such, I had wanted to put quite a few more slides here, but unfortunately, this is a crazy period of time in most educational institutes, as many of you would know, because this is the time when we submit grades, moderation, and horrible things that are associated with that. Okay, so please, yeah, I've spoken enough. Questions, queries, Ania?
Sir, I have a query. If we adopt these transformers like to images, Preeti, I'm asking a question. Like if we adapted these transformers to images, we divide our image into patches. But if we want to adapt it to time series, like most of the people they are using for these transformers for nowadays for time series also. Here in language, we have words which we are saying tokens. For words, we design embeddings and then we perform the self attention and we do multi ed attention. But for other domains, how do we design these tokens at the basic level? Because this thing is not clear. People are matlab using these transformers everywhere, be it any domain, but they are not able to comprehend how that is actually the basic level, how these tokenization is done for, let's say, a time series data or something. Sir, you are mute, I suppose. Your voice is not audible. Hello? It's not audible, sir. Preeti, can you hear?
Yes, ma'am.
Okay, okay. Maybe some network issue on my end. I'll just go out and see. Some problem at my end and only.
Madam, it may be a problem at my end also. Let me try this
No, no,
again.
sir. It's now audible. We have network issue in our department. I just came out.
अभी देखते हैं
Yes, sir.
कि
आप बिल्कुल सही आ रही है बिल्कुल. I am
बिल्कुल सही
outside,
है.
sir.
It's actually something that we call the computer science solution. कि उसको बंद करें और फिर लगा दें तो उसके आसार काफी अच्छे होते हैं कि वो चल जाए.
जी 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 बिल्कुल.
जैसे वो जसपाल भट्टी वाले उसमें उस एपिसोड में था ना कि रेडियो चल नहीं रहा था और गुस्से से रेडियो को फेंक दिया जमीन पे एंड सडनली साउंड स्टार्टेड कमिंग आउट ऑफ
Yes.
वैसी हालत है. मैडम जो सवाल किया था इस तरह से
जी
वो अगर अगर अध्यापक को जवाब ही जवाब है उसका अंदाजा रहता है अध्यापक क्या कहते हैं गुड क्वेश्चन. ठीक है वरना 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 वही होता है कि हाँ मैं कल बताऊंगा या थोड़ा पढ़ने दो. तो दैट सॉर्ट ऑफ थिंग. तो Dr. Jain, I'll say that that was a good question. The answer actually, funnily enough, is that this is more natural. वो ज्यादा स्वाभाविक है. Because typically, let's say in time series, इमेज तो छोड़ दीजिए, टू डायमेंशनल डेटा है, पैचेस. ये उसको भी किसी तरह से लिनियराइज करते हैं, एक लंबा सा कॉलम वेक्टर बनता है. बट लेट्स से वी हैव गॉट लेट्स से स्टॉक मार्केट ट्रेंड्स. तो उसमें यही है कि जो जैसे निफ्टी वो इंडिसेस हैं स्टॉक मार्केट के. टेक दैट एज अ फीचर वेक्टर. द थिंग इज दिस इज मोर नेचुरल. ये ज्यादा स्वाभाविक इसलिए है बिकॉज आई कुड फॉर इंस्टेंस डू व्हाट पीपल इन कम्युनिकेशन कॉल वेक्टर क्वांटाइजेशन. मतलब वो अनसुपरवाइज्ड लर्निंग करते हैं. टेकिंग लेट्स से आई टेक all the stock market data of let's say size 10. What I do is in 10 dimensional space I do clustering. जैसे ही वो क्लस्टरिंग कर लिया उसके बाद जैसे सादा क्लस्टरिंग किया जैसे आई डू के मीन्स let's say I do k means clustering. So what I take as the representative point of the cluster, that becomes my concept. So that becomes the token which is
Okay.
associated with all the things. So actually for numerical values, it's slightly easier. This is in fact, madam, what you have raised is actually a very deep question, which actually says why before 2012, before Mikolov came up with the word to vec paper, before
Mhm.
that it was not clear for computer scientists to actually use neural networks. It was on
Exactly.
exactly
Because the
this
word
semantic issue.
embeddings were not there.
एग्जैक्टली मतलब वो स्वाभाविक रूप से हाउ कैन आई नेचुरली assign a set of numbers or assign a vector to a concept of a word. So with these it's possible to assign it naturally. But for
Sir.
data like stock market data, like time series data, or let's say images or videos, it's very natural. Okay, बहुत स्वाभाविक रूप से आता है. So that is the
Thank you, sir. Thank you, sir, for clearing my doubt.
अरे
Thank
नहीं
you so
मैडम ये
much.
तो बहुत ही गूढ़ बात आपने कही है.
जी, thank you so much, sir. Any more questions, participants?
We can see that Bhopal has some lovely weather nowadays.
So, yeah, it's very pleasant here. Not too cold, but it's
हाँ
pleasant
जी हाँ
now.
जी.
रात को
अब तो
थोड़ा
अभी
रहता
समुदाय
है.
के बाहर हैं.
जी जी आई एम आउटसाइड द
हाँ
डिपार्टमेंट
हाँ
बिकॉज
वो दिख रहा
इनसाइड
है
वी
आप
हैव
सब हो.
सिग्नल इश्यूज. मैं रूम में ही बैठी थी बट आवाज व्हेन आई आस्क्ड द क्वेश्चन इट वाज ऑडिबल बट व्हेन यू वर आंसरिंग आई कुडंट हियर
No
एनीथिंग
madam,
सो
it
आई
could be a
जस्ट
problem at my end also.
ओके.
We can't trust computers nowadays.
चलिए. Okay then, sir. We'll wind up the session. Thank you so much for
बहुत
accepting our
धन्यवाद.
invitation.
श्योर
आपको भी
मैडम.
बहुत बहुत धन्यवाद sir. Thank you so
मिलते हैं.
much. Thank you. Thank you.
नमस्कार.
Preeti, you